Alright, so this is for today, our little graph analysis. First things first, you just need to cut it along the lines. You don't need that crap at the bottom. I was just too lazy to kind of get rid of it. I'm cutting this as you're watching this to show you how quick and easy this is. It should not be something that involves too much brain power. I'll probably mess it up and I'll be embarrassed, but that's okay. I guess I cut it like that. I don't know. I'll figure out how I want to cut this. Alright, so I have it like that. I'm going to cut it and put it into my notebook. So, let me see my blank page I have here. Where's my tape? I don't see this tape. Tape that down. The tape along the sides. A little too short on the side over here. Oh, nuts and bolts. Oh well. Cut it there, and I'm going to cut it, or tape it there, sorry. So let's see, I have one flap, two flap. I just don't have these as flaps, but I guess I can just make them into flaps right now. Do. Gosh, this thing sucks some days. Oh. Alright, so if you just did anything crazy like mine, you now have 4 flappy wappies that go along with what we're going to be talking about. Looking at these, they should look somewhat familiar. You might, it really just doesn't matter if you have time along the x-axis or if you have time along the y. In this case, we have time along the y-axis. They both are going to be showing this at the same time. So just kind of right at the top, these are distance / time graphs. Okay, I know this is graph analysis, but it's just really kind of a task analysis, just a task that you are doing. You'll probably see one of these on your NCFE, and really graphs should not scare you. They should just be something like, oh great, another stupid graph. Let me just interpret it, get what I need to get done. There's no title for these. Okay, that's the first thing you should always notice when you look at a graph is what is the title. The second thing you should look at is what is along your axes. In this case, we have distance. We don't have any units or anything like that, but in this case, you don't really need it. This could be minutes, seconds. This could be miles, kilometers, feet, meters, anything like that. On a standardized test, though, you will probably see these distance in meters or kilometers, time, minutes or seconds, because that really doesn't matter. But this first one, it is straight, steady line that's increasing. So it's saying that at 1, let's say, second, let's say these are meters, at 1 second, this object is at 1 meter. Okay. At 2 seconds, it's at 2 meters. So it's pretty much traveling at 1 meter per second. Let's just say that. So this is going to be, let me just double check, because I'm always afraid I'm going to mess these videos up. So we'll just say it is fast increasing speed, and it's at a constant rate. Okay, and I'm saying constant rate because I'm looking at it. Here's 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. It's a constant rate. It's increasing by the exact same rate. So let's say these are meters. 1 meter per second is the rate at which it's traveling. So that's a pretty easy one to kind of grasp. Looking at this one over here, we see, again, the y and x-axis are exactly the same. Y to the sky is how I remember it. Distances across. So looking at this, so it's not the same as this graph over here. It's sloping. It has an upward slope. So I'm just going to put upward slope. Okay, so we're not going to say it's at a constant speed this time. So let me just make sure my graphic organizer matches up what I'm telling you, because Lord forbid I do something crazy. So let's see, at 1 second, here's my time. 1 second, here's my distance. Again, I think I said this was meters. So put this in seconds, because I always forget. Meters and seconds. So if I'm looking here, at 1 second, I'm not even, I would say I'm at a half a meter. At 2 seconds, I'm at 1, or excuse me, 1 second, I read that wrong, 1 second, I'm used to time being on the x-axis. At 1 second, we're at 2 meters. So at 2 seconds, we're at 3 meters. So I just went from 0.5 to a full 1. If I'm looking at my distance increasing by time, at 3 seconds, I'm now at 4 meters. 4 seconds, I'm at 5. 6 seconds, or 5 seconds, I'm at 6 meters. 7 meters is at, 7 meters, I just jumped up to 7 seconds. So there's a kind of a big increase here. And that's where I'm kind of noticing, okay, so we went from, in 1 second, we went not even, 1 meter in half a second, 2 meters in 1 second, another meter in 3 seconds. So just looking at this, I see that there's a big jump between here and here, so an upward slope. So that to me means this, if there's a slope like this, because it kind of was steady, chugging along, it was kind of steady, but all of a sudden it slopes upward, and that slope upwards means that it's increasing in speed. So increasing in speed. So maybe you just checked your Waze app and you saw that there's no cops in sight, so you're going to hit the accelerator. Probably not a prudent decision, but hey, people make mistakes. You're increasing in speed. Okay, whatever this object is, maybe it doesn't have, let's say, elevation out here, so maybe it's now going downhill. So it's going to increase its speed as it's going downhill. Now this one's pretty much the opposite. Well, in this case, we're at 5 seconds already. So it's kind of different now. We're looking at this one. We're at 5 seconds. Okay, so again, I'm going to put like a little chart down here. So time and distance. Because sometimes I'm a visual person, so I can look at it like this and still kind of like, ugh. So at 5 seconds, I'm at how many meters? I'm at 1 meter. Where am I at 4? So at 4 seconds, so I don't feel like doing increments. So at 4 seconds, I'm about a little bit, what are we at? 4 meters. I'll say 3.9 meters. Actually, it wasn't quite 4. That's okay. Actually, I'm looking at this. Where it crosses the 4, it's actually past 4, so I should probably cross that out. I'll put 5 point, let's say, 3 meters. This penny makes mistakes. Sometimes I just do these on the fly, much like I'm doing right now. 3 seconds. So, 3 seconds is just about at the 6 meter mark. 2 seconds. Where am I at for 2 seconds? Just about 7, let's say 7.2 meters. It's not going to be 100% accurate. And then at 1 second, I am 8 meters away. Okay, great. Well, what does this information tell me? That as time goes by, they're getting further and further away. So, what does this data tell you? So what exactly does this tell me? This tells me that especially this dip right here, there was deceleration going on. So you're still traveling. You don't just come to a stop. If it was a stop, it would be right down here at distance. But it's going downward, it's sloping at a pretty heavy rate. And then it's kind of slowly decreasing. So you saw the cop right here. You're like, oh, bleepity bleep. You hit the brakes pretty hard, but you don't want to come to an exact stop. So you're still slowing down. You're still going a distance. However, you traveled a little bit further out in a shorter amount of time, so you were definitely decreasing. So this is a decrease in speed. That's all that pretty much means. When you see a downward slope, it's pretty much the opposite of an upward-facing slope. Oh, if it wasn't blurry the entire time, that'll make me upset. So, downward slope. Anytime you see a slope like this, like a little ski slope, you're having a change in speed. Okay. All right, now let's look at this guy. Here's our last one. So again, we have time and distance. Time is on our y, x is on our x, or distance. Distance is on our x. That's funny. Hold those times. It's going to bother me. Let's see. So looking at this, we do time and distance. I'm looking at this here's my time over here. And let's say this looks like 1.7 seconds. Where are we at? 1.7 1.7 seconds. Gee, huh. 1.7 seconds. What does this mean? 1.7 seconds. So we're looking at it here. We're looking at it. We're still at 1.7 seconds. We're at, let's say, 1 meter. 1.7 seconds, we're at 2 meters. 1.7 seconds, we're at 3 meters. So my time isn't changing, but my distance is. This is kind of wonky. So I'm looking at this. What does this mean? All right, so looking at this one, I just took a break to Google search it because this is really throwing me for a loop. Usually, distance is over here and time is down here. Because this doesn't make sense. How is something moving, but yet it's staying at the exact same time? And copying this out of a book provided by Tucker Creek, I can't quite figure out what this is. If I graph my data, because if you look back at your graphic organizer, okay, the usual way that I'm used to seeing this is that distance goes along the y-axis and time is along the bottom. So when you see a straight line and distance is on the side, meaning it's not moving, but time is going on, so time is still transpiring, it's not moving. But they have it reversed on here, which is, this one just puzzles me, because I don't think this is accurate. If anyone could prove me wrong, by all means. Because time is going on, or time isn't going on, but the distance is going. So it's not like it's a ball moving. And it's not like an object is just staying there because the distance is changing. So this one befuddles me. I have no idea. It doesn't make sense because it rationally cannot be explained. If someone can explain this to me, please do. It makes sense if this was distance over here and this was time, but it's not. And it's not like I cut it wrong because distance of time is up here. So this one is a puzzle. Ta-da!